Dear colleagues, if you are ready, we can start our lecture. I suggest to wait several minutes for other participant, and then we will start. Okay, all participants are here, and I suggest starting my lecture. I will show you some presentation. Okay. Today I would like to tell you about some kind of sheet metal forming operation which is called incremental sheet forming, and such operation, such technology can be treated as smart manufacturing. And later I will show you why this technology is smart, and why traditional sheet metal forming technologies are not smart. I want to start with some examples of traditional sheet metal forming technologies. Here at the slide you can see technology for production of cups. So if we want to produce a cylindrical cup, cylindrical part from sheet metal, we need to use the following tooling. We need a punch, blank holder, die, and of course blank, the sheet metal which is formed into a cylindrical cap. By applying force on the punch, we draw the sheet material through a hole in the die, and as a result received a cylindrical cup. If we want to receive a cup of smaller diameter, we can divide this operation in several steps. And lower you see a picture of multiple dip drawing, when we decrease the diameter of the cup, which was produced on the previous step, and such process, repeating this process, we can obtain a part of desired diameter. I want to show you some video of this process so you can understand how this occurs in reality. It's example of production cylindrical cup. Here you can see round blank. This one, this is blank. On the upper part is a die. Here is it's opposite to the shim that you have seen on the picture. On the picture, the die was at the bottom. Here the die is on the up part. This is punch, and the black one is blank holder. At the moment, the blank is drawn through the hole in the die. Now it's a reverse stroke, and here you can see a cup. Yeah, so from a round blank, we have received a cylindrical part. Now, from this cylindrical part, we can receive the part of a smaller diameter. The principle is the same. On the up is punch. We use the part obtained on the previous step. Black one is a die, and here we didn't have any blank holder. So the cup is drawn through a hole in the die. And as a result, the diameter of the cup is decreasing. Using this technology, we can receive parts of different shapes. So here you can see the simplest one, the cylindrical cap. But of course, the shape can be different. If we are speaking about automotive industry, it can be parts of a car. For example, hood inner or wings of a car. And if we are speaking about aerospace industry, by such technology can be produced different parts of aircraft, rockets, and so on. What is the main disadvantage of such process? The main disadvantage is that we need a big amount of tooling. So we need at least punch, die, and blank holder, 3 parts. And if we are speaking about mass production, for example, automotive industry, where we need to obtain the big number of parts, so the cost of such production will not be very high, because the cost of tooling will be divided on the number of the parts. And for example, if we are speaking about thousands of parts or millions, billions of parts, the cost of tooling is not very important. But if we are speaking about... Данил, можете принять приглашение там? And if we are speaking about aerospace technology, aerospace industry, where the number of parts, the quantity of the parts is not so big. For example, if we are speaking about rockets, we produce not so much rockets per year, 10 rockets, 20 rockets. And for such number, we don't need a mass production. It's small bench production, or even some parts can be produced only as one part. Yeah. In this case, the cost of production tooling is very high and is very important for our technology, because the cost of some dies and punches can exceed thousands of dollars. It's very expensive to produce such parts, because they are produced from expensive tooling material, high-strength steels, and they produce by machining. So it's very expensive to apply such technology for aircraft and rocket production. Moreover, the equipment which we need for such parts also very expensive. Here on the slide, you can see two examples, two types of equipment which is used for traditional sheet metal forming technologies. On the left, you can see double action mechanical press, where the movement of the punch is created by movement of the crank. Yeah, by rotating the crank, we create a vertical movement of the punch. And on the right, you can see hydraulic press, where the movement of the punch, for example, up one, is created by hydraulic cylinder, and by creating here pressure, we move the punch, and as a result form our part. All of the and on the video which I have shown you was used such press, single action hydraulic press. So depending on the sizes of the part, the sizes of the presses also differ. For example, here you can see example of some German hydraulic press. It can be very big, big equipment, have a big sizes, and moreover, such equipment is also very expensive. Such presses cost millions of dollars. Yeah, so it's very expensive. And of course, if we are speaking about mass production, the cost of these presses, of this equipment, may be not so important, because we will divide the cost of this press by number of the parts, and it will not create a big increase of the cost of the part. But if we are speaking about airspace, rocket industry, aircraft industry, of course, it will increase the cost of the part if you produce only one part per year, for example, and it's not suitable for small bench production. So, what is decision from this? What is the decision how we can solve this problem? We need to use new technologies, smart technologies, which can allow us producing parts first using cheap and universal equipment, and second with some universal tooling. When for a big amount of different parts, we need the same tooling. So at this case, the cost of production of such parts will not be too expensive. One of such technologies is incremental forming. What is the idea of such technology? I will show you the video, but at the start I would like to show the principle. So you have a sheet of the metal, yeah, you can imagine that this sheet of the paper is a sheet of the metal. Yeah, if we will fix this sheet on all boundaries by using some clamping, yeah, we have fixed it, and then we have a punch. Yeah, this pen is a punch. Yeah, it has not so big sizes in comparison with the sizes of the sheet. Yeah, and this tooling is universal. Yeah, it's suitable for all parts and for all operations. And if our list is fixed, we can move the punch to the sheet and make a forming operation by movement of the punch step by step. Yeah, for example, on the left, you can see the example. We create a force by a punch, deform sheet, but locally, yeah, deformation is not very big. And then we move the punch in a such path that this path should coincide with the shape of the part. Yeah, I'll show you the video, and I think that it will be clear. Okay, here you can see on the upper part, this is punch. And here is a sheet of the metal, which is fixed on its boundaries. Yeah, on the surface of the sheet, you can see some oil. It's need to reduce friction between punch and the sheet and to produce a part with a more smooth surface. Yeah. You can see that punch make a punch moves, and by each rotation, it also moves into the axial direction. Yeah, it pull the sheet to the bottom part of the screen. So the path of the punch, path of the tooling repeats some 3D spiral. It's moved by Galilean spiral. Of course, you can see that this process is not so fast in comparison with traditional process. But this disadvantage is not very important if we are speaking about small bench production. For us, is more important the cost of the technology, but not the time which we will spend on the production. So at the moment, you can see how some conical part is formed. I will go to the end steps. So if we will change the path, the movement of the punch, and this movement will the same as the shape of the part, we can produce parts of quite different shapes. What about equipment? What equipment we need to use this technology? There are several options. The first one, we can use industrial robot. It's today it's quite wide use type of equipment. We can find this equipment, I think, at every big factory, and using industrial robot, we can produce parts by incremental forming. In this case, the punch is fixed on the flange of the robot, and arm, by moving arm of the robot, we form the part. The second variant, which is very close to the industrial robot, is using of Stewart platform or Gexapod. It's also a variation of industrial robot, but in this case, the movement is created by hydraulic cylinders, and the shim of the fixing such platform can be different. On the right, you can see example of such technology. Also here you can notice that in both cases, for industrial robot and for Stewart platform, we use two robots. So we have robot on opposite sides of the sheet. Later, I will tell you about this approach and for what types of part we need to use two robots. And the last one is using standard milling machine. It's here. And also by creating controlling program for milling machine and fixing sheet inside this machine, we can form different parts. What is difference? The main difference about these different types of equipment is accuracy of parts which we produce by incremental forming. The accuracy depends on the rigidity of the equipment. The more rigid, the more axis of freedom have equipment, the higher will be tolerance of the produced part. And in this case, the smallest accuracy will be obtained by using industrial robot. Stewart platform provides higher accuracy, and the highest accuracy, the highest tolerance of the part will be produced by milling machine. What types of the parts we can produce by such technology? The geometry and shape of the parts is just unlimited, and here you can see different examples. It can be different crosses, hexagons, cones with different geometry, and so on. Here you can see examples of not big parts. Yeah, it's small one. Of course, this technology can be used for bigger parts. In this case, we just need robots or milling machines with bigger sizes. Yeah, the bigger part we want to produce, the bigger sheet we need, and the bigger dimension sizes of the equipment we need. And here you can see different examples. For example, this is some prototype of hood inner for car. It can be prototypes for some aerospace industry, for products for domestic usage, some designers elements for architecture of buildings, for example. Yeah, this sheet, some kind of sculpture, for example. Also, it can be used for production of some musical parts. Here it's Stellas, and for medicine application. For medicine application. Данил, а как принять приглашение? One moment, please. Okay. If we are speaking about mass production, for example, automotive industry, of course, incremental forming technology isn't suitable for mass production because we need to produce a big number of parts at a small period of time. But if we are speaking about prototypes of some new cars, yeah, and if you use incremental forming technology as rapid prototyping technology, in this case, it's very good technology because we don't need to spend money for a very expensive tooling, yeah, and we can produce prototypes in a very short period of time and see good it's for production or not. And the same situation is with medical application. For example, creation of implants for head or creation implants for dental medicine is also limited, that implants should be personified, yeah, for each person, for each man. The shape and sizes of the implant depends on the physiological features, and we can't produce the same parts for every person. Yeah, in this case, we can use also incremental forming, and these parts will be suitable only for a concrete man, concrete person. Okay. What about technology and features of this technology? There are several variants of different incremental forming technologies. The simplest one is asymmetric incremental forming, where we need only blank holder, yeah, on the right, on the left, and on the right you here see blank holder and some forming tool, punch. And the movement, the path of the punch, as I have said, is defined by some controlling program, about which we will speak, I will tell you later. What disadvantage of such process? Of course, if we form and change geometry of the sheet in some part of the sheet, for example, in the middle, as here on the picture, yeah, these areas are free, and by creating pressure and applying forming force here, we will also create deformation of these regions. Yeah, it can be both plastic or elastic deformation, but all of these factors will not provide us a high accuracy of the part. Yeah, the sizes will have deviation from the desirable geometry and the shape. And on the last stage, we need to apply some calibration operation. How can we improve this technology? We can use single point incremental forming. In this situation, we use some back plates. Here it's shown by red color. Yeah, these back plates are fixing the sheet, the free areas of the sheet. Yeah, for example, boundary, external areas, and in this case, this part will not bend, and the black plate will increase the accuracy, but the accuracy will increase mostly at the periphery of the shape, of the geometry. So the next step for increasing tolerance and improving accuracy of the part is using of two-point incremental forming, for example, with petal die. And of course, each technology will be more complex in comparison with previous. Yeah, here we have also tooling, blank holder, but in this case we also have petal die. Petal die is some kind of specialized tool or mold, and it partly repeats the shape of the geometry of the final part geometry. Yeah. By locating this part in the areas where the accuracy or the tolerance is the lowest, we can increase in these areas the accuracy. Of course, we can go wider, and instead of petal die, use a complete die. Yeah. In this case, this complete die shown by red is completely the same as the geometry of the manufacturing part. In this case, the accuracy will be very high because the sheet is drawn, is stretched by a punch, by a forming tool, is stretched on this geometry. What is the disadvantage of such approach? The disadvantage that we need a complete die, and complete die is very expensive if we are speaking about small bench production. And for aircraft or airspace application, it's not good solution. Of course, in this case, we have only die. We don't need a punch. I mean, not this universal forming tool. Yeah, I mean punch which repeats the geometry and the shape of the part. So this technology at least will be twice cheaper as traditional one. But in any case, we need a complete die, and it's not good. How we can partly solve this situation? We can produce die not from steel, yeah, not from steel, but from some cheaper material, for example, from wood or plastic. In this case, the strength of this punch, wooden punch or plastic punch, will be enough for production of a small number. For example, we can use such die only for several times. And of course, it's much cheaper than to produce this punch from steel. What is next variation of incremental forming technology? It's duplex incremental forming technology when we are using supporting tool. And this supporting tool is moving, yeah, and always creates some this tooling acts like backplate on the previous technology, but in backplate incremental forming technology, backplate was fixed. Supporting tool is also moving and increase the accuracy on the also external or peripheral areas of the blank. And in this case, we need also to use some equipment for this supporting tool. We need in some way to move this supporting tool and also create a controlling program for movement of this tool. And in this case, for example, we can use the second industrial robot. when I have shown you equipment, variants of equipment for incremental forming, and you have seen that there was 2 robots on the opposite sides. In this case, one robot is used to move the punch, the forming tool, and the second one is used to move support tool, red one. How we can improve this approach? We can use 2 punches. The standard punch forming tool and the local support tool, or the opposite punch. Yeah, it's also duplex incremental forming, but here we have 2 punches. And for both of punches, for gray one and for red one, we need to use industrial robot. In this case, also there will be 2 industrial robots which will stay opposite each other, and between these robots will be a sheet of the metal. What is the main advantages of such approach? In this case, we can increase the tolerance of the part, the accuracy very high. And the second one, we can change thickness of the part. During the production, during the forming of the part, we can control the thickness and create the geometry where the thickness will vary. In some areas, we can keep some, for example, we can create a bigger thickness where the, for example, part will be loaded by very high forces. And in some regions, we can create a part with a small thickness. And for example, these parts will not need to be very strong. As a result, we can decrease the weight of the part, which is very important for airspace application, where each kilogram, not even kilogram, each gram of the mass of the rocket is very important. Okay, here you can see a comparison between 2 approaches. On the left, the tolerance accuracy of the part produced by duplex point incremental forming with PATL support tool, and on the right is the same but with opposite punch, with counter punch, with local supporting tool. And here you can see advantages and disadvantages of both technologies. Of course, the higher accuracy will be if we use local supporting tool. But comparison 2 parts produced by different technologies, you can see that application of PATL supporting tool does not provide high tolerance on the concave areas. Yeah, larger deviations will be in concave areas. So if our part does not have such areas, then we can use these technologies with PATL supporting tool. And if our part have such areas, then we have to use technology with local supporting tool. So both technologies is appropriate for complex geometries, but this one is appropriate for mostly symmetrical concave surfaces, while incremental forming, duplex point incremental forming with local supporting tool is appropriate for geometries with both concave and convex areas. Next part is how we can create tool paths and what types of tool paths we can use. There are several approaches. The first one is alternating. You can see it on the left on the slide. So our punch is making circular movement. It moves by circle. And when we are going to the next step, the direction of the movement is changing. For example, the first step, the punch is moving counterclock, yeah, and the next step, when the punch have been moved in axial direction, in direction of z-axis, it's moved counterclockwise, and so on. When the punch goes from one step to another, it moves diagonally in the xz axis. Yeah. So this axis is z, and the axis x in x, y are lay in the plane of the sheet, of the initial sheet. Yeah. So when we are going from one step from another, we are going deeper into the sheet. The punch will move diagonally in the plane xz. The next type of the tool path is contoured. Yeah, you can see it on the right. The principle is the same, but the direction on each step will not be changed. So if you started move counterclockwise, we will repeat the same movement on each step. Yeah, and as a result, we will form the final geometry. What other parts we can compare? The next is stepped. The difference from the previous one, from contoured, is the direction, the movement of the punch between steps. In the step, the movement of the punch between steps, when the punch goes deeper in the sheet, is in the XY plane. Yeah? So we make a round, and when we are going to the next step, the punch first moves in the XY plane. It moves to the center of the conical part. Yeah? It's first one, then we go in the radial direction to the center, and then punch moves in the Z direction. Yeah, it's form part. It moves into deeper into the part, and then makes another circle. And this process repeats continuously. What is the difference between the stepped movement and the previous one, contoured movement? If we are using contoured movement, on the form part, you will see the line. Yeah, this movement creates line where the tool moved from one step, from one level to another. So it will be a conus, for example, with a line. It's not so good if we need a high quality of the surface. This line is visible. And if we use stepped movement, the part will be the same, but there will not be will not be line on the surface of the part. Next variant of the tool path is helical. Yeah, here you can see it shown on the right of the slide. I think it's clear. In this case, the punch is moving, and its path the same as helical. Yeah, it's spiral, but in 3D. Yeah, so we screw the punch into the sheet, and it simultaneously moves in 3 axes: in x-axis, y-axis, and also z. So we create helix pattern in the form part. Next, what we should understand, what is forming tool, what type of forming tool we can use. There are different shapes which is usually used, and all of them you can see on the slide. I will start from data punch. Yeah, so it's a ball. The diameter of the ball can be different, and a cylindrical pad. It's mostly use type of the punches for incremental forming, and it have only one disadvantage, that the strength and rigidity of this punch will not be very high. Yeah, it can bend in this part, and as a result, application of such punch will decrease the accuracy of the pad. How we can prevent this? We can increase the diameter of the cylindrical pad, and as a result, we received a straight punch. So it's cylinder with a hemispherical end. Of course, the strength and rigidity of this punch will be higher. If we need, in some cases, more strength punch, we can use tapered pad. Yeah, in this case, we use not straight, yeah, not cylindrical pad here. It will be conical or tapered. And for pads where we need to form some geometry or shapes with a small radius, we can use tipped patch. Yeah, the advantage of the sponge is a very small radius of the end of the tip of this sponge, and the all other part of the punch is made with a bigger diameter, of course, to increase strength of the sponge and increase its rigidity to produce a more accurate parts with a high tolerance. Different punches on the video which I have shown you was used, for example, straight punch. What about secondary or supporting tool? In these cases, there are two options. The first one is support tool, and previously I have shown you how it can be used and how it helps us to increase the accuracy of the pad. But also we can use heat gun, for example. So on the opposite of the sheet, in the place of local deformation, in the place where the punch is situated, on the opposite part, we can place some heating device. It can be, for example, heat the pad by hot air, or it can heat pad by electrical current. Yeah, we can heat the workpiece, the blank, locally, and in this way we are increasing the formability of the sheet metal, and as a result we can produce pad with a bigger deformation, with bigger strains. For example, if we are using heating gun, and heat the blank with hot air, yeah, we also need to move this heat gun, and this movement should repeat the movement of the principal tool. It's not very easy because we need, for example, the second robot. How we can solve this problem? If we are using heating by inductivity, by inductive currents, yeah, we can apply current to the punch. Yeah, on the punch will be, for example, one wire with electrical current, and the second wire will be connected with the blank. Yeah, in this case, it will be created flow of the current through punch and the sheet, and this will hit the sheet locally in the place of the contact between punch and the sheet. And for example, if we are speaking about such high strength materials as titanium alloys, which are widely used in aircraft and rocket industry, of course, it's good heating the sheet, because such materials usually don't have a very high formability. And heating can greatly increase their formability and allow us to produce the parts with a big strains, big deformation. Next step, frame design. The last step, we should understand how to fix the sheet. In this case, we usually use some frames. These frames can have different design, but it's also very good when we can change the sizes of the working zone. Yeah, the sizes of our blank. For example, here, by moving the parts of the frame, we can fix the sheet of the sizes 24 inch per 12 inches. And if we use another frames, yeah, the frame is the same, but the parts of the frames will be different. We can increase the working area. As a result, put here, fix here the bigger sheet and received a bigger part. And sheet usually is fixed by some toggle clamp. You can see it here with a red part. These clamps, these toggle clamps, fix sheet between some wooden or metal frame. It can be different, and some supporting shim. It also can be metal or wood. It does not matter. So the sheet is fixed between frame and shim by a toggle clamp. When I have speaking about different kinds of supporting tools, I have said that the formability of different materials also differs. For example, steels have a higher formability than aluminum alloys. Aluminum alloys typically have a higher formability in comparison with titanium alloys. What I mean under formability? Formability is ability of the material to deform plastically, to undergo plastical strains. And of course, at some moment, if the formability isn't enough, we will receive cracks. For example, here on the conical part, you can see a crack failure at the end of the conus. Yeah, what is the reason? Of course, if you have a sheet material and this sheet material is fixed on the boundaries, yeah, and we are changing the shape of the sheet, increasing, for example, creating here a conus, yeah, we change sizes, but the volume of the sheet, of course, stay constant. Yeah, the volume of the sheet does not changes, but we are increasing the surface of the sheet. Yeah, I think you agree with me that the area of the initial sheet, of the initial surface of the sheet, is smaller than area of the part. And if we are increasing area of the initial sheet, but the volume is constant, the volume stays the same, what will change? What size, what dimension of the sheet will change? How do you think? as you can see from the slide, the thickness of the sheet will decrease. The sheet, when we form it incrementally, will undergo thinning. Yeah, it will be thinner, 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 and at some point, the thickness will be very, very small. Yeah, like here, the thickness will be very small, and the thickness will not be enough. The thickness will not be enough to undergoes a big load, because a punch creates a force, yeah, and it's like tension of the sheet. The thinner sheet more easier to tie it one part from another. So during incremental forming, the thickness of the part, the thickness of the sheet will decrease, and this thickness will depend on the angle, yeah, on the angle of the part. If we are speaking about conus, it's part with a constant angle. Yeah, it will be the same on all height of the part. But some parts can, with a complex geometry, can have some areas with different angles. And usually the incremental sheet forming is limited with 65-degree angle. Yeah, so the limiting parameter is 65-degree. We can't produce parts with a bigger angle. So if we are speaking about incremental forming, traditional incremental forming, we can't produce cylindrical cup. Yeah. So when the angle of the wall is 90-degree. And of course, we can calculate, theoretically calculate the thickness at the bottom of the part using some quite simple formula. Yeah, it's here. We should multiply the initial thickness and cosinus of angle of the wall. And I think that you should ask me if the limiting angle is 65 degrees, so this technology is not applicable for some big number of parts. Yeah, we can't produce parts, cylindrical parts, but we have a solution of this problem. We can use multi-stage forming. So on the first step, yeah, for example, we can create part with the wall angle 50 degrees. Then on the next operation, we increasing this angle 60, 70, 80, and the last one is 90 degrees. And as a result, we will create part with just we will produce just cylindrical part. Of course, this will take more time, because for each step the technology will be the same. We have a punch which moves, if we are speaking about axisymmetrical part, which moves round by round and forms the final geometry. But we can use this technology for complex part, and where we need to produce parts with an angles higher more than limiting angles. Okay, I have ended with the first part. I will show you video how this technology is sorry. How this technology is made at our university. So first step, what we have to do, we need to create a control program. Yeah, we need to say robot how to move, and the movement of the robot, the tool path should repeat the final geometry of the path. For this purpose, we are using some standard software, SprutCAM. This software usually is used as a CAM program, computer-aided manufacturing program, and is used to create controlling program for milling machines. Nevertheless, we can use this program for programming our robot. Yeah, so here you can see how our engineers create this program. Yeah, we are firstly in some CAD software, for example, in Unigraphics, computer-aided design software, we are creating geometry, the shape of the part. Then we are importing this geometry in the SprutCAM software, and in this program, as a result, we received a controlling program for robot. Here you can see as an example of this program. Yeah, it's a list of coordinates, x, y, z coordinates of the robot. And also you understand that robot consists of several arms. Yeah, it can move in different axes, in 6 axes, and each arm of the robot has own movement. Yeah, so we need to program each arm of the robot, each axis of the robot, how it moves. If we will make this manually, it will take plenty of time. So for this purpose, we use, as I have said, SprutCAM software, and this software automatically program each arm, each axis of the robot. Yeah, here you can see that we are transferring controlling program from a computer, from SprutCAM software to control panel of the robot. At our laboratory, we have KUKA robot. Here we are uploading the program to the robot, and here you can see tooling which will be used for forming the part. Yeah, here we use straight tooling. It can have different diameter. Then we are fixing the tooling on the flange of the robot. Yeah, it's quite simple. Then we need to fix a sheet at our frame. Here we use a sheet, dimensions of the sheet approximately 200 millimeters per 200 millimeters. And as I have shown you at the presentation, at the slide, we use some clamping devices for fixing the boundaries of this sheet. At the moment, our engineer fixing the sheet on both, on 4 sides, 4 boundaries of the sheet. It's the last one. And then we are initiating our robot, and robot starts moving and approaches to the starting position. Yeah, here is the robot at the starting position. Then we are also applying some oil, some grease on the surface of the blank to decrease friction, because friction creates some additional forces, and we need to decrease these forces. And also application of grease allows us to create a more smooth and more finer surface. Yeah, and here you can see as the robot starts its movement. Now the robot moves according to the program which was previously created using SproutCam software. We can change the speed of the process, and at the moment the robot moves on the lower speed to control and to understand that it moves according to the program and everything goes good and fine. Yeah, here you can see the movement in the program. Yeah, and the robot should make the same, but in the reality. Okay, it's not so fast. I will speed up. Yeah. Here you can see that from initial sheet we have formed or pulled some conus. Here you can see the opposite side. It's the opposite side of the frame, and you have seen that here in these parts on the corners the initial sheet have
включать видео не через демонстрацию экрана, а через демонстрацию вкладки.
А мне сказали так.
Лучше иначе. Потому что, видишь, оно иначе тормозит. То есть у тебя оно воспроизводится нормально, а здесь, если можно.
Ну, не проблема.
Просто будет чуть-чуть лучше качество.
Да, следующее видео так включу.
Да, все окей, хорошо.
So you can see that by waiting this process, we can obtain parts of different shapes. Here you can see some hemispherical, conical parts. And for example, more big and complex parts, which have different shapes at different areas. Yeah, this is example of some pyramid. All of these parts were produced by incremental forming. Now, for example, Sichuan. Да, я понял, я включу. Вот здесь вот через это я закрою, да, и там вкладка, там вариант есть. Okay, I have ended with the first part of my lecture. Next part is some practical one. So if you would like, we can make some small break, maybe 5 or 10 minutes. It's up to you. Yeah, if you need a break, write in the chat. And the second part of my lecture, I will show you how to create controlling program in the CAM software. And then you have an opportunity to create your own programs. You will have some access to our computer, to our software. And I will show you how to use this program. And I suggest you to repeat my steps, to choose some parts and make a controlling program for these parts. Then we will try to produce these parts. And on the last day of the summer school, we will show you examples of the parts which was produced by your program, the program that you have created. So what about break? Do we need break or not? Please write in the chat. Or if you have questions, you also can ask me using microphone or writing in the chat. Yes, in the chat I see questions that the cylinder is preheated or something to relieve stress, or is it called molding? Of course, after forming, we can use some annealing, so we can heat the part to some temperature to decrease the residual stresses and to decrease the strength of the part. But it depends on the final application of the parts. Sometimes we need to do this operation, sometimes no. Okay, so at the moment we have a 10 minutes break. I think most of us want to make a break, and then we will start again. So 10 minutes break at the moment. We are starting. It's left several minutes. Okay, I think everybody is ready. We can go to the next part of my lecture. On your screens, you see the desktop of the computer. To this computer, you will have an access, yeah, by some link. I think this link you already have, or this link will be sent to you later. My idea that I will show you how to create control program for robot for forming part. Also, you will have the link to this video, yes, and at any moment you can repeat and see what steps do you need for making the programs, and this will be your tutorial and your help. Now I will show you this video and make some comments. We can start. So the first step, you should open a folder. This folder is created specially for you on the desktop, and in this folder, you should open the file with the name new. Yeah, this file is created specially for you. And by opening this file, you are starting the special software SprutCam. Yeah, on the screen, you can see the name of this software, SprutCam. Okay, then we are waiting for loading this software. The program opens, and here you can see the welcoming screen. You can close it, or you can close it and go to the next step. You can drag on the right of the screen. You have some working zone, yeah, and inside this zone is created the 3D model of our robot and the frame. And using right, left buttons on the mouse, yeah, you can drag this area and find the robot. At the starting point, the robot is placed in some corner, and you should drag and move the area to place it in the center. And also, by using the wheel on the mouse, you can increase or decrease the picture. So next step, you should push path stroke. Yeah, unfortunately, this program hasn't a good translation into the English. So some some options and menus on the interface are in English, while some menus are in Russian. Yeah, so you should see on your tutorial video and compare. You choose the first stroke. Here in Russia is written path. Yeah, the first step, we need to import the geometry of the path which we want to create. So you are clicking path and then click the import button. Yeah, it's up here, import button. By clicking this button, there will be opened the window in which you should show the path to the file with geometry. Yeah. Later, I will show what types of paths you can choose, and all of these geometries are saved at the same folder. At which we have started and opened the file with the name new. Yeah. So here you can see we have imported the path, and this path is appears in the working area. I will make a pause. Here you can see that this path is placed not correctly. Yes, you can see that we need to rotate this path. At the moment, robot is here, it's the punch, yeah, and the path should be in this plane. At the moment, the path is situated in such way, yes, and we need to rotate it to the starting position. And the next step after inputting the path to the program is to place it in a correct position. Yeah, for this we use transform button. Yeah, by using the buttons on the right menu, we can remove the robot. It will disappear, so do not. So we can see only path. The first, we need to move the path to the center of the local coordinate system. Yeah, you can see we have moved the path to the right. Of course, we need to make measurements, but for our practical case, you can make this by eye. For us, it's not so important tolerance of the final path, so we can make this by eye. The next, we need to rotate. Also, we have pressed the transform button, have chosen another menu, and have rotated this path by 90 degrees. Yes, at the moment, the path is situated into the correct position. Next, we need to center this path. The local coordinate system should be in the middle of our path. Yeah, and also we will move the path using transform button. But in this case, we will move along another axis, Y axis. Also, you can make this not very accurate. But here, using program, we also can make measurements. Yes, for example, using ruler, we can measure distance between different lines, between coordinate system and some lines. And in this way, we can measure and understand how we have to move, how we have to move the part to make it centered. Yes, so the distance between these lines is approximately 76 millimeters. Yeah, and the distance from the left line to the coordinate system should be then half of this distance, yeah, of the 76 millimeters. After calculations, we can understand the distance for displacement of the part. So after we have placed and centered the part, we are going to another step. We are choosing another menu, and this menu shows us different machining operations which are usually used. And of course, as I have said, the SprutCAM software is used for milling operations, and we are using this software for not standard purpose, not standard application. From this wide variety of different operations, you should choose finishing 3D helical operation. And after you have chosen this operation in menu, on the right, you can see the example, how this operation is fulfilled. On the right, you can see some animation and understand how the tool will move. Okay, so we have chosen operation, and here in the tree, you see this part. Okay, I will make some back. Okay, еще. Yeah, so you push create this operation, and then we need to show for a program what surfaces we need to treat. Yes, we are going to another menu and choosing surfaces of the part. You can choose them by clicking one by one, or can drag a box and choose all one at one step. So next step, we have chosen the surfaces. Then we need to put the parameters of the process. Yeah, parameters for robot. For example, next step, we should add the value for step. What is mean step in for incremental forming? You understand that when the tool is moving at each level, at each step, our tool can have different displacement. Yes, for example, in radial direction, it can be 1 millimeter, 5 millimeter, 10 millimeter, and in that direction, it also can be different. So by changing and putting this value step, we are giving the value of displacement of the tool between stages. Usually, this step is very close to the thickness of the initial sheet. For example, here we have a sheet thickness of 2 millimeters. Yes, and the step should be lower than the thickness. According to this, we have put 1 millimeter. You also should put 1 millimeter. We have used for production of your parts the same sheets with the thickness of 2 millimeters. So if we have put 1 millimeter, the punch, when it moves, will displace in radial direction and in axial direction per 1 millimeter. 1 millimeter per step in radial and axial. So when it make one turn, yeah, it will displace in radial direction per 1 millimeter and in Z direction, axial direction also per 1 millimeter. Next parameter. Next parameter is the bottom level or ending position. This position should coincide with the end of the path. Yes, so this distance is equal to the height of the path. If we have a path of 50 millimeters, this distance should be also 15 millimeters. You can use a ruler to measure this position or make it approximately. So next we are giving bottom level. Top level is 0. Then we should put such parameter as safety level. What is the safety level? Okay, I will make a pause. Yeah, here we are putting safety level 200 millimeters. I advise you to use the same value. And here you can see right square. And the square is situated on the distance of 200 millimeters from path. What is safety level? When you are forming a path, yes, your punch is moving. And first step, the punch should go very close to the sheet. Then it starts forming operations, create a path. And then the robot have to remove the punch to some safety distance. Yes, and this removement should be made not by some random path. Yes, the best way is to move it straight by a horizontal line. So we have form a path, and then the robot moves the punch on the distance equal to the safety level, 200 millimeters. And after this position, he can move in a random way to return to its initial position. So you also give the value equal to 200 millimeters. It's from practice, we have chosen this distance. Okay, go next. Next, we need to simulate the operation. We are pressing run button, and SprutCam, the software, calculates the path of the robot. By moving this leveler, we can change speed of the process. It changes only animation speed. Yes, it's not real speed of the movement. It's just speed of animations to see how the path is formed. And you can see if it's going okay or not. Yeah, as a result, we can receive the path, the shape and geometry of which is the same as geometry we have imported. After we have checked the simulation, we need to save the controlling program in the format which is suitable for robot. Yes. So, okay, I will go some steps ago. Here, you are choosing the name of the file. this file will be then saved and transferred by flash card to the controlling pult, controlling device of the robot. You should save this file in the same folder at which we have started. And you should give name. No, name of the file can be up to you. Yes, it does not matter. You are giving name of the file, giving save, pressing save button, and then run. And on the right appears the listing of the programs, and these programs can be read by KUKA robot. And also previously, you have to choose, it's somewhere here. Yeah, on the left, you have to choose the model of the robot, KUKA robot. Yes, here on the left, you are choosing KUKA robot. Because for different equipment, for different robots, the controlling program have different output format. Yes, and if you say in another format, not KUKA robot, this file cannot be read by our robot. Okay, so you are saving, pressing run. On the right, you will see, as I say, the listing of the program. Pressing exit. And closing program. Okay, I will go step. When you are closing file, here, when you are closing program, SprutCam, yeah, SprutCam software, the program will ask you, save changes to new or not. You should choose no, because you will divide in some teams, yes, and teams will have access to the program at different time. And the new file is one for all of us, yeah. And if one team will save the new file with your changes, yes, the other team cannot work with this file. So you save only output file for KUKA. It was for KUKA robot. It was previous step. And when you are going out from the program, you should not save it. Okay, it's clear. If you want to save the file in SprutCam, you should use the option save as. Yeah, save as options will allow you to rename the file. It's some standard way. I think in the main menu you will find themselves this button save as. Yeah, and in this way you save and changes the name of the file and does not rewrite the initial file. Okay, it's clear. Have you any questions concerning work with software? Or it's clear?
Yes, it's clear.
Okay. What parts you can choose? In the folder, which is on the desktop of our computer, which we have opened to open new file. Also, folder with samples geometry. Here you can see these geometries. So these geometries are quite simple. Yeah, it's hemisphere, conical, pyramids with a different number of edges, cross geometries. And the first one is geometry which was used for writing the video. Yes, it's the same. I note that the most difficult part in creating controlling program is properly place the path. It's the step when we have rotated it, move it, and for these geometries, for these different geometries, the transformation and placing the part in the correct position for all of this part will be different. Yes, so the displacement in different coordinates need you to rotate or not need depends on the geometry. So when you open, you will see and understand if you need to use rotation or not, need you move it in X direction or not, the same in Y and Z directions. So you should see and decide what operation, transformation operation you should apply. All other steps are typical for all of you. Maybe the different, not maybe, the different value of bottom level will be for these geometries, the bottom level will be different because the height of these parts are also different. So you need to give different bottom level. Unfortunately, here should be the link and the schedule, but at the moment I think you have some of us have tried remote access to our computer. Organizers of summer school will send you the link, and also they will send you the schedule of remote access. Yeah, you should divide into teams. It depends on you how you will divide into the teams. We have 6 geometries. I think that you can divide into 6 teams. Yes, and each of the team will have access per time to the computer and will create the controlling program. If I'm not mistaken, each team will have 2 accesses. Yes, one time, for example, 1 hour, for example, tomorrow, and 1 hour at Saturday or Sunday. Organizers will send you schedule of the access. So you are creating a program. You have video, link to the video, how to create the program, and also you have link to our today lecture, where there will be comments on this video. At least at Sunday evening, you should complete this task, and on Monday we will start. We will check your controlling programs, and we will form parts from according to your program. So at the end of the school, we will show you these parts, and of course we will make some video of the forming process, and you will see how parts made by you will be produced. For today, I have ended. If you have any questions, please ask. Or write in the chat. Okay, so if there are no questions, I was very glad to show you this lecture, to show our experience in production of parts for airspace industry, and I hope that you will easily make controlling program, and we will show you results of your work at the end. Bye.